Okay, let's get a start. Please take a seat, guys. Okay, welcome everyone to the second day of the SIGIR program. Today, it is my great pleasure to introduce our second keynote speaker, Professor Thorsten Joachims. Thorsten is a professor at Cornell University and an Amazon scholar. Most of you will certainly know Thorsten, right? His pioneering work in IR has had a profound impact on how we understand and develop search and recommendation systems. He's particularly well known for his contribution to learning to rank, which has been a cornerstone in the development of modern search systems. This is exemplified by his SIGIR 2016 Test of Time Award for the paper Accurately Interpreting Click-Through Data as Implicit Feedback, which was published in SIGIR 2005. So now, on a personal note, I'm sure you all have your own research heroes, and certainly Thorsten is one of mine and of my PhD students' research heroes. I still remember when I was doing my PhD, I still remember looking at the work of Thorsten, and my work at that time was on a more esoteric topic, so not related to learning to rank, yet Thorsten's work had a big influence on me because it made me understand the importance of sharing and opening our methods into software libraries. And I'm sure you all are well familiar with library that Thorsten has written, like SVM Rank or SVM Lite or SVM Struct, and they're porting from those original C libraries to more modern IR systems. And so I'm sure you all can relate on how the availability of that software enabled your work or your teaching in IR. Okay, it's now time to sit back, relax, and be inspired by today's keynote by Thorsten, which is titled Towards Steerable AI Systems. So please join me in welcoming Thorsten.
Techniques also allow us to build new systems for applications that weren't even on my radar a few years ago. So I've been thinking about what Gen AI means for my own research agenda. And I think many of these observations also carry over to the SIGIR community more generally. So what I will try to make in this case, in this talk, is the case that the expertise that we have in the SIGIR community is going to be crucial for building this next generation of interactive AI systems that include Gen AI. And I hope that SIGIR will embrace this mission. So let me start with providing a bit of historical perspective. So IR was driven by these applications early on where it was libraries, it was analysts, information analysts, where kind of the whole complexity of language and complex information needs came together. And IR didn't go the route of overly formalizing this, but instead tried to deal with the whole complexity of these problems as a whole. The methods and the kind of empirical rigor that came out of that then really took off kind of mid-90s when the web came, right? Then all of a sudden we had these commercially highly relevant applications like search engines, recommender systems, e-commerce, news distribution, where these techniques, we refined these techniques into what I would call interactive AI systems for the purposes of this talk, that were able to learn by interacting with people, that were able to personalize, and that were able to act intelligently. And I argue these are the biggest AI systems that we have in the world today. And then I think we're at another inflection point today with Gen AI, both because it provides new affordances for these systems, and we're already starting to include Gen AI into these existing systems. But then also there are these new applications like chatbots, writing assistants, maybe assistants for our own research or tools that will process our insurance claims, that I think are really a natural progression of interactive AI systems that the SIGIR community was instrumental in building. And I think we should be instrumental in building this next generation as well, because we have the expertise to build it right. Okay, so what do I mean by interactive AI system in a little bit more formal way? At a very abstract level, there is this kind of abstraction of a contextual banded loop that we're executing, right? So for example, what I mean by that? So like in the search ranking applications for e-commerce, we have a context that's a query. That's like a command given to the system. Then the system responds intelligently with an action Y. In this case, it's a ranking of the products. And then the system sees feedback of some form. So things like clicks or purchases or add to carts on this particular action that the system took. Or take a recommender system, right? There, the context would be a profile of that user. And maybe the action that we're taking is what to put into this top banner. So here, the show alone, which, by the way, is a great show. I really like that show. Good recommendation for me. And then you get feedback. The system gets feedback, clicks, like, do I actually watch the whole season? How do I rate it? And so on, right? And this feedback is what we can use for learning. But now with Gen AI, there's a lot more types of actions that we can take. So for example, for that show, there's this little snippet that could be explaining, personalized to me, why I should be watching this, what I'm going to like about this, right? And again, I can then see feedback of, do I actually watch the season, right, and so on. So more complex actions that the systems can take, often in the form of language, but also more complex inputs that the systems can take. So for example, I recently gave to Amazon Music Maestro system, it's a Gen AI system for playlists, the kind of context or query that I wanted a high-energy soundtrack for running in a park in Germany that used to be a steel factory. And it created this playlist for me, together with a title and also a snippet kind of explaining what it is. And it's a pretty good playlist. I liked it. And again, we get feedback on this, like listening time skips and things like that. And then there's whole new other applications that are, maybe you're thinking outside the scope of SIGIR, but I want to make the case that they're actually very similar to what we've been building all along. So for example, a writing assistant that would kind of draft emails for me to, so that I can respond faster, right? It's a little less clear what the feedback here is, right? We have a context, we have an action, not clear what the feedback is, but I'll go into depth on this particular application and show that it really is very similar to the types of problems that we already know to handle. Okay, so in this talk, I want to kind of make 3 big points, or kind of organize around 3 thoughts. The first one is that for many of these kind of new problems in Gen AI, I think we already have the expertise and algorithmic tools to approach them. They're not going to be identical, but I think we can take a lot of the things that we already know and bring them to bear there. And one example that I'm going to give is how do we personalize large language models through interactions. The second is, well, we may not have all the answers yet, but at least we've gotten ourselves a couple of bloody noses in building this last generation of AI systems, right? So, and one example that I explore is this kind of conflict between the short-term signals like engagement that we know to optimize really well, but that we actually have long-term objectives like customer satisfaction. That's what we really want to optimize, and how we can make that bridge. And then the third one is, there's a whole range of affordances that Gen AI provides. And I'll explore kind of especially the use of language in increasing transparency and also instructability of Gen AI, of the systems that we already have. All right, so let me start with the first one. How can we personalize large language models by interacting with users in a natural way, right? And I would argue that this is probably that's the only way that I think we can really kind of personalize these systems, because it's very hard to, like, on an individual basis to get otherwise training data for these systems. Okay, but maybe let me first kind of ask the question, why would we actually want to personalize LLMs? And let me tell you about a study that we are currently doing, and we've partially completed. Looking actually into how do LLMs actually write, or who do they write like? And a good data set for that is college admission essays, right? It's very personalized writing, and it comes with interesting kind of tags, right? So like we know kind of the race, the gender, socioeconomic status of the person writing the text. So we can now also ask like a large language model like GPT-4 to write a college admission essay and then compare against the human written ones, right? And it turns out that in many ways, these LLM-generated essays don't actually sound particularly human. So there's big differences in terms of style, like in the use of verbs, for example, and in the use of complex long words. There's a lot less variation, and there's probably a lot of corporate policy that goes into exactly how these systems talk, right? And it's not clear that you really want to sound like that, right, when you write your college admission essay or when you answer your personal emails. But if anything at all, these systems sound more like the kind of high socioeconomic status students. But really, they're actually quite distinct. So this is, on the right, this is actually a t-SNE embedding of all of these essays, some human-generated, some LLM-generated. And what you can see is that they actually cluster quite neatly, right? And partly it's that the LLM essays are actually all kind of self-similar. So this is a t-SNE plot, so kind of nearest neighbors matter. And you may argue that, well, actually you have to tell the system a little bit about yourself, right? So maybe we should tell the system, oh, this is a student, white, male, and so on. If you do that, you get the blue points down there. It doesn't make the text any more kind of human-like. It actually, if anything, it makes them more stereotypical in a character of, especially for minority groups. So, okay, so I think if you actually want to kind of keep an authentic voice, you probably want to have a personalized SVM that actually talks like you, not like one of these standard models. So what would that look like? So for example, here you may have a kind of a writing assistant for your email, like class email. I get a ton of questions like this. Professor Joachims, can I have an extension on my homework since my pet rat is sick? And here's a draft that the Gen AI system could have produced, right? Probably wouldn't accept that like that. I mean, it's actually true. It probably was like retrieval augmented system that got the policy from my course homepage. First sentence I probably wouldn't write. It seems kind of negative, especially since actually, well, I do say that I don't give extensions, but everybody has 7 free late days, so it's basically everybody has extensions. So I wouldn't write that first sentence. I would probably add a word of sympathy at the beginning, especially since my family also has pet rats. This is Ralph and Momo, very cute. And I promised my kids to work them into this talk somehow. There we go. And then kind of the last sentence, I don't want to be quoted on, you can miss one homework. Don't want to be quoted on that one. I want everybody to do all their homeworks, but it's no big deal if you miss one, because one gets dropped. So that's the kind of feedback we could actually get for free at a large scale. Right? So what is that? I would argue this is pairwise preference feedback, right? Think of machine translation, English text, German draft translation, fix it up, it's a slight improvement. But in both cases, you can't say that this is, the Y bar is the perfect translation or the perfect answer to the email, right? I spend a certain amount of time on my email, and I would not want to, claim that this is the best way I could have written this. Now, this actually fits into an online learning model that's called coactive learning. And I think what we know well in the SIGIR community is kind of connecting kind of the machine learning with the human factors that generated the data. And this coactive feedback model kind of assumes that we have a boundedly rational user. And what this means is that the user has a certain budget of kind of effort he or she is willing to spend on creating a solution. And so here in this case, there's the set of all possible whys, all possible actions or responses the system could take. We start the user at this point yt, and then the user has a certain effort budget to explore a neighborhood of that. And then picks an action that's kind of the best one in that kind of neighborhood budget, right? So that's a boundary rational user that at some point satisfies this and uses y bar as the solution. So you can model that as the user having utility function in his or her head, and that the user returns a y bar that has a utility that's higher than that the system provided. But you can't assume that the user gives us the y star, the overall utility maximizing email or whatever it is in that whole space. So this is a weak pairwise preference feedback that we're getting. And originally that model was actually inspired by recommendation. In particular, if you think about how you maybe pick a show to watch at night, right? You kind of start with some recommendations, you browse around for 5 minutes, and eventually you pick a show that's kind of the best one among the ones that you found. That's your kind of region that you're using, but it's not the optimal show. You haven't looked at the whole catalog. Or for ranking, right? If you have that query, system provides you that action y, that ranking y, and then you see that the user clicks on maybe that link. That's a bounded exploration of the results. And you would get a slightly improved ranking if you promoted that link by 1 position, let's say, right? Then you have this ranking is better than that ranking. Again, but it's not the optimal ranking, right? You haven't labeled everything, right? Or haven't judged for relevance everything. So a little bit more formally, this is coactive learning is an online learning model where you have a boundary rational user, has this utility function in their head, where we now go through this loop that we have a context. The algorithm presents a y. The user returns a y bar of slightly higher utility. And then we measure regret by, what's the utility difference between the optimal action that we could have taken and the action that the system actually took. And we do that even though we actually never observe cardinal utilities. They only exist in the user's head. And we never, or don't necessarily get the optimal y star. We don't get to see that, right? So this is one online learning model that's common here, right? Maybe one of the less common ones. And there are many others, like there's the expert model where we receive cardinal feedback for all of the actions in hindsight. There's the very popular bandit model, right, where we see the utility in a cardinal sense for the action that we took. There's the dueling bandits model, which is also a pairwise preference model, but the algorithm presents 2 options, and the user just says, this one is better than that one, right? And then there's the coactive one, where the algorithm presents 1 option, and the user constructs another option, y bar, that has a higher utility. And you can probably think of other models of kind of interaction and learning that we have developed in this community. Okay, so how do we solve this coactive learning problem? There's actually a very simple algorithm. That's the whole thing. It's called the coactive preference perceptron. And what it does, it makes the assumption that the utility function can be represented as a linear function. So there's a feature vector, phi of xy, that describes the match between query and action. And then what we want to learn is this weight vector w, right? And the algorithm is then just a typical perceptron, almost, right? We observe the context. The algorithm then predicts, for the current guess w that it has, predicts the action that has the highest score according to that w. That's that argmax here. Obtains the feedback y bar from the user, and then does this update. It's a perceptron update where it kind of changes the w so that the utility of the y bar kind of gets increased, and the utility of the y kind of gets decreased a little bit, right? And you keep doing that over and over again. That actually, if you make some assumptions on the quality of that pairwise preference feedback, you actually get nice regret bounds for this. So the way to formalize the quality of the feedback is through this psi approximately alpha informative condition, which basically says that in expectation, the feedback that we get, the y bar, has to have higher utility than what the system predicted, and not just infinitesimally more, but kind of closing the gap by some factor alpha to the optimal. Alpha can be small, but you have to get a little bit closer. And you can have model error as well. So if that linear model isn't correct, you just accumulate some model error. If that is if your feedback has that property, well, any feedback has that property, but it just depends on the model error. So then you get that your regret is bounded by the model error that you have. You can't reduce that. But the second term, that actually converges to 0 at the same rate as if you had y star feedback, right? Just by a factor of alpha slower. So that's actually, that shows you that it's very efficient from a learning theory perspective. It's actually very efficient feedback. Okay, so we know that this works. So this is one experiment. It's one of my favorite experiments, so we run the archive full text search. And, we ran this experiment where, so there's a retrieval function between the archive full text search that has about 1,000 features. And it's a linear model, so each feature has a weight. So it's exactly the same as we had for coactive learning, right? So we need to learn this 1,000-dimensional weight vector W. And we used as coactive feedback that same strategy that I had before, right? If you clicked on this link, then the ranking where this link is one promoted is slightly better, and that's how you get these pairwise preferences, right? So how do we evaluate? So we had some hand-tuned W that was running on the system before. What we did was we always ran some iterations of coactive learning, and then one iteration where we computed the ranking for the hand-tuned W and the ranking for the current W learned by coactive learning, did an interleaving between the two, and then looked at which of the rankings won this side. And what you can see is that very quickly, you get like a win ratio of 2 to 1, which is very big for interleaving comparison. So this was actually very kind of effective learning. And this was an ICML paper. And so this graph is in the ICML paper. And we kind of, submission was sometime in January. So this is the state of the system in January. And then Karthik, the main author of this paper, I remember, and we were talking, and at some point we realized we never turned this off. We had forgotten that. And so Karthik pulled the data, and this is what had happened over the next half year. We had the system had just continued to learn, stayed stable. There were bots coming through, new papers being added, all kinds of crap happening, right? But literally, this is the first system that I've ever built that I could forget for half a year, and it would just intelligently and autonomously continue to learn and act well. So I think this is a nice example that if you have kind of a reasonable feedback model that connects well to what your users are actually doing, and then you have the right algorithm with good theoretical guarantees, you can build very robust interactive AI systems that way. Okay. But linear models are not going to cut it for personalizing LLMs, right? So how do we do this for now LLM training, right? So clearly one thing that we need to do is we need to replace that linear model by something like a transformer network, right? But then the rest of the algorithm, in a way, is actually quite general, right? So the second step, this is an inference step. It's basically pick the Y that has the highest score out of the current model. If it's a linear model or a transformer model, in a sense that doesn't matter. It's just computational complexity is different. And then the last step, if you think about it, what a perceptron does, it's a gradient update. It's a gradient step for a particular loss function. And so Well, can we replace this with a gradient step for a loss function that's actually kind of appropriate for a transformer network? And basically, that's all of what we did. So we replaced the linear model with a transformer. So we would have a policy pi. That's our LLM policy. And it's a KL regularized policy so that it doesn't diverge from like producing proper language. It's regularized against a base model. And if you have a KL regularized policy like that, there's actually a closed form solution of the reward or utility function that it represents. And that's the second line. It's one of the tricks. And then the algorithm is almost the same as for the perceptron. Basically, what you do is you take the argmax of the utility under the current model parameters. Now that you can't compute, you can't just enumerate all of the y's anymore. This is all possible pieces of text, right? So what we do is we just take a Monte Carlo sample and optimize over that. And then that update step, if you look beyond the math, what that really just is, it's called DPO. But what this really just is a Bradley-Terry pairwise preference update that I think everybody or many people here are familiar with, right? We've used that many, many a times, right? So, and you can even salvage some of the theory. No a priori guarantees anymore for a deep network, but still. Okay, so I think this is a great example where you can take existing results and kind of generalize them to these Gen AI with the techniques that we're very well familiar with. Does it work? Well, this is a standard benchmark. There's more in the paper, kind of completing IMDb reviews with positive sentiment. And what you can see, basically, so this is now kind of trying to replicate some gold standard LLM. That's what we say is our user here. It's much easier than generating kind of human-driven coactive feedback. And it has the property that you can now look into the kind of head of that model and actually use the cardinal reward of that model for evaluation. So what you can see is that even for like weak feedback, like very low alphas, just very small improvements in these pairwise preferences, you get LLM models that better and better optimize the reward or optimize the utility of the teacher. What you can also see here in that paper, we do the same for the dueling bandit setting, which may be more important for kind of a writing application like this, where you have short pieces of text and you just pick one of those. You can do that as well, similar techniques. And I think there is a lot of we have, and how do we make this tractable even for these Gen AI applications? All right, so that was maybe the first part where I think there's one example of techniques that we have developed in this community, but I think that transfer to Gen AI, and I think there's a lot more. And as I said, the second part is about things that we already know are tricky. So we don't know what the solution is, but we at least know some of the problems to avoid or where some of the pitfalls lie. And so I remember quite distinctly, so I wrote the first paper on learning to rank and optimizing ranking functions based on clicks in 1996. And I remember distinctly that I was super excited about it in a sense that this is now a way of taking all of the distributed kind of knowledge that everybody has and that they convey through their clicks and aggregating them in these big intelligent systems. And to some extent, that was right. But in some extent, that was also really naive, right? Once, there's economic incentives behind, where you're being ranked, right? Then there's there's gaming of the kind of feedback and of the clicks. There is irrational behavior that people have. There's even, all the way to being, self-harming behavior in terms of addiction behind this. So I think we kind of start to understand this. And I think the one thing that I want to kind of drill a little bit deeper into in this space is we know really well how to optimize short-term objectives like clicks and engagement, but we also know that what we really want to optimize is these long-term objectives, like user satisfaction and retention and things like that. And how do we do that, right? Let me give you one example where this trade-off is really apparent. I think you can all kind of find examples in your own work. But one example is, for example, if you are a music stream service, and you have to compose like a front page like that, then people tend to kind of listen to the same music over and over again, right? If you want to maximize clicks, then a sure bet is to just kind of present the music here that you know that customer has already listened to in the past. Now, that's good. It provides some navigational benefit to the customer, but it also makes for a really boring service in the long run, right? The customer would never discover anything new, and after a while, they would probably just not come back and cancel their subscription at some point, right? So what you want to have is you want to make sure that people discover new and exciting music in your catalog, but every time you do that, it comes at the expense that it's a risk, right? You're going to get fewer clicks that way. So there is this very apparent kind of conflict between kind of the short-term engagement maximization and kind of long-term making sure that the customer finds enough interesting content. So one way that I like to think about it is that the algorithms that we have become really good at microeconomic optimization, right? Exactly these contextual bandit things where we take an action, we see the feedback, and then we optimize which actions we take to maximize that feedback, right? We get this rapidly, we get a ton of it. It's really important, it's really useful, but only to a certain extent, right? Certainly, if you don't get any clicks, that's a bad sign. But getting more and more clicks at some point is not necessarily saying that this becomes a better and better system. What we would really like, and I think everybody agrees on that, is that we want to kind of optimize more macro-level metrics, something like user satisfaction. We want to keep our supplier pool of a certain size and happy, right? We want to avoid polarization, all of these things. And we may even have some ideas of how we can, interventions that would achieve this, like exposure allocation and changes to that, or, putting in more diversity or novelty. But I think we are lacking the language and the tools for actually making sure this connection top down to the bottom actually gets executed. Right? How do we actually do that? And it's a little bit like, and what we're trying to do is we're trying to fiddle with the short-term kind of metrics down here. But I think that's really, really hard. It's a little bit like, flying an airplane. I came from Germany to DC by changing the voltages somewhere in the fuselage, right? You can probably steer the airplane that way. I don't recommend it. Probably wouldn't get on that airplane. But what we would much rather, but what the airplane actually has is multiple levels of abstraction and control, right? You always have a controller that you give a command to, and then you trust that that controller executes that command in with the best possible trade-offs, right? So that at the end, you can have a pilot sitting up front where the pilot really doesn't have to worry that much. You can basically type into the autopilot, keep it in straight and level flight and go to DC. I think we need these levels of abstractions in our AI systems as well to actually control them and steer them. And I don't think we have that right now. So, we've been thinking about how do we build this kind of levels of abstraction where we can give macro interventions from on top through an abstraction barrier and can be sure that they get, at the next lower level, get executed executed as we specified, and with the least kind of cost to the short-term metrics, right, in our case. And we already potentially know what these metrics, these macro-level metrics are. So for example, we may want to have an intervention that says, on a weekly basis, for me, there should be exposed to at least tau many new artists, right? And that tau could be something that's personalized to me, right? Or it shouldn't get more than 3 push messages. Or for the item perspective, maybe the items from a particular supplier get a certain amount of exposure, right? These are all kind of constraints that I can pass down through this interface to then have executed at the micro level, and hopefully at the least cost to my micro level metrics, right? So what's the key problem here? The key problem is that we have a mismatch in timescales, right? At the macro level, things happen on a week basis that we get this feedback, happen on a session level or individual ranking level, right? And it's unclear how we do the credit assignment, right? And so what we're proposing is to actually literally use control, just like you would use in a physical system. So you can think about this, you have a very simple case here, that maybe we have this one constraint that says, well, we could have many of those, thousands, that says, make sure that over the course of a week, Thorsten gets to see tau many new artists. And now I can track that line, right? I can track that line so that at the end of the week, I'm kind of at tau. That's my target. And then I see that there's a certain state that I have, and that I deviate from that target, and that's my error. And now my controller tries to reduce this error, and it tries to do it by minimizing, whenever I kind of push more kind of novel artists, that comes at a loss in click-through, for example, loss in engagement. And so what I really want is I want to minimize this loss in engagement, so the surface of this red area, while it's still, at the end of the day, ending up at my target tau at the end of the week, right? And now that controller now provides me a way of bridging these timescales, like the weekly timescale at the macro level and the session timescale at the micro level. So how would we do this? You can think about it a little bit like a constraint optimization problem, where we say, over the course of the week, find me the rankings that maximize DCG subject to the constraints, all of the constraints that I have. I get enough new recommendations, you get enough new, and so on, all the thousands of them. But of course, that doesn't work, right? We can't just, at the end of the week, make all of our ranking decisions. No, we have to make them on the fly. So it's not like an offline optimization problem that we can solve, but we have to solve it online. But that we can do. So here's one way to do it. So you take that optimization problem, you turn the constraints through Lagrange multiplier into this Lagrangian, and you have these lambdas now, Lagrange multipliers. And then you can use techniques from online convex optimization to solve this optimization problem in online fashion with appropriate guarantees. So in the very simplest case, what you can do is, so whenever you have a ranking that you want to optimize, you solve this penalized argmax. So it's kind of a penalized argmax of the predicted click-through rate, how much progress you're making to the constraints, fulfilling the constraints, with these Lagrange multipliers lambda, kind of providing the penalties. And now you are kind of on the fly adapting all of these penalties through these online convex optimization methods. In the simplest way, this could be just a gradient update. And so there's a wide range of literature that we can now use to build these controllers to connect these different timescales. We can also build in planning there, right? So for example, if you have a good idea that I'm more willing to engage with new artists over the weekend, then you can build that in, right? Instead of tracking that kind of diagonal line, you could track a different line that kind of says, okay, focus more on the weekend. And that way, you can actually get the same macroeconomic target while minimizing the loss in engagement here. So you can build all of these controllers. But what I think what's most valuable about this is that it provides a layer of abstraction, right? Now you have this controller that basically you can trust to fulfill the constraints that you put in, these taus, right? And now you can have, for example, at the macro level, another contextual bandit learner that as actions has taus, right? The parameters of that controller. And at the macro level, this bandit maybe learns only on a weekly basis. And maybe it optimizes the weekly visits of that customer. You see that only once per week. Very sparse feedback. You could never learn rankings from this sparse feedback. But you don't have to learn rankings on that sparse feedback. You only have to figure out what's the right tau. And that's a much, much smaller action space that you can hopefully still address even with the kind of sparse feedback that you get for a certain time period and can be sure that the system does it. That goes all the way to regulatory policy, like the kind of Facebook settlement that Facebook needs to show housing-related ads by demographic parity. That's a constraint that you can put into a controller like that, and then the controller can figure out how do I fulfill this constraint with the least loss of engagement. All right, so that was the second part, some of the challenges that come up where I think we at least know what's hard and maybe have some idea how to address them. And then I think there's this third part about all the interesting new affordances that Gen AI brings to our systems. And I think one that I want to talk about is the kind of idea of using language to make our systems more transparent and instructable. So one way that we know how to do really well is personalization models, right? And they, at an abstract level, they all have this kind of encoder-decoder kind of setup where the encoder takes the past ratings or whatever it is of the user and then produces a kind of summary profile for that user. And typically that's like a 50-dimensional vector, right? And then you have a decoder that uses that user profile to then make predictions for the other movies that we haven't watched yet or other items we haven't engaged with yet. And we can do that for rating prediction, for click prediction, for next item prediction, for all of these things, right? If you think about it, matrix factorization fits into this. Variation autoencoders fit into this. Two tower models fit, lots of models fit into this. But one problem with all of this is that users being represented as a 50-dimensional vector is almost by definition not transparent, right? It's very hard to actually, convey what this 50-dimensional vector means. What's exciting about Gen AI is that we now have kind of ways of, working in language, right? And so what if we made our representation of users not a 50-dimensional vector, but actually a piece of text that describes what the interests of the users are? So then our encoder becomes an LLM, and that language-based profile is something that what Radlinsky and al. Call a scrutable model, right? A model that kind of almost by definition is transparent. People could even edit it, and in cold start you could come up with something that you could put there, right? You can. And note that this is different from an explanation, right? It's not an explanation of a 50-dimensional vector. This is on the causal path, right? If you make a change to this piece of text, it will change the predictions, right? If you make a change to an explanation of a 50-dimensional vector, it will change nothing, right? So can we build systems like that, right? That actually work in language this way? And so one kind of ongoing piece of work that we're currently doing is to think about how do we train such a system, where you have an encoder LLM that produces a piece of text, and then a decoder that in the simplest case is just an embedding model that now takes the profile piece of text and item descriptions, comes up with a score and maybe sorts them in a ranking application. So here, this would be for next item prediction. Can we train such systems? And the answer is, yeah, we can do that. So One algorithm that's actually very convenient for this, in collaboration with a colleague of mine, Wen Sun, we developed this training algorithm called Rebel. Fits this use case quite nicely. Again, you learn one of these KL-regularized LLM policies, and you get this nice closed form reward for that. That's associated with that. And the algorithm is also, again, very simple. What you do is, from your current policy that you're trying to optimize, the encoder LLM, you sample two profiles, P and P prime. You give both profiles to the decoder, and you compute, what is the, let's say, NDCG of this profile and of that profile. One of them is probably going to be better than the other. And then you do a gradient step that's actually very simple. You take the, you try to match the difference in NDCG that you observe with the predicted difference in NDCG by your LLM model. And then you minimize the squared error. And if you keep doing this over and over again, then you get some nice convergence guarantees for that. And if you do that, you can actually train the encoder LLM. So this is training steps here, and performance goes up. You can train the encoder LLM to produce kind of text-based profile summaries that give you better and better NDCG, right? So we can train this, basically like we've been training these other embedding models where people were 50-dimensional vectors. You can also, train the other side, the decoder, at the same time, right? So you can do this Rebel type of training for the LLM, and then the decoder, that's just an embedding model that has profiles as well. And so we train that with kind of noise contrastive loss, which basically is just, a cross-entropy type objective trying to predict which is the correct next item. And if you do both kind of interleaved, train the LLM, train the decoder, you get something that, as expected, works even better. Here's one of the profiles that kind of comes out of this, right, after the training. It's actually a reasonable, readable profile, right? It lists some of the high ratings, lists some of the stuff that the person didn't like, and then has a kind of an overall summary, like heartwarming, uplifting, nostalgic, with a focus on simple yet meaningful stories. So that's certainly something that, much more interpretable than a 50-dimensional vector. All right, but I think there's much more that Gen AI can bring to the systems that we're building here. So let me wrap up. And so I think, I hope I could make the point that SIGIR has really been instrumental in building the AI systems that we have today. And in particular, this kind of AI systems that are interactive, right, that work with people, that react to people. And that I think SIGIR has a crucial role to play for not just the kind of bringing Gen AI into the existing systems that we have, but also kind of adopting these new applications. These are still, like writing assistants, these are still information systems. They have very similar structure from the system that we have been building. And I would hope that SIGIR embraces these new applications as well, because I think it's very relevant to this community. So, and with that, let me just thank my collaborators again, and I'm happy to take questions.
Wow, what a great keynote. Thank you so much, Thorsten. That was very inspiring.